So next up, we have Sergey Levine. And without further ado, Sergey.
Great. Thank you. So this is going to be a very kind of application-focused talk. I wanted to tell you guys a little bit about some ideas in robotics and how concepts in reinforcement learning can be applied to robotics in the age where we train big models on very large data sets. And I want to talk about the role of prior data for learning motor skills. So I'll get down to like actual low-level motor skills towards the end of the talk, but I want to start with something maybe a little bit more general. Let's start with a little thought exercise. Let's imagine that we're building a robot whose job it is to go and explore another planet. And that's kind of a good way to prime how we can think about autonomous agents. So that there are some things that it needs to do that are very low-level kind of motor control things, but there's also a lot of kind of uncertainty about the kind of situations it'll encounter. So we need to prepare this robot, if it's going to go to another planet, to deal with unknown and unexpected situations. It's like a little bit like if you imagine a person trying to survive on a desert island, right? Like they're going to approach that situation with prior knowledge, prior experiences, things that they already know how to do, but they also have to be very flexible and adaptive. They have to change their behaviors based on the needs of the situation. And I think that's how we should be thinking about AI agents. They have to bring to bear prior knowledge, a set of skills that will allow them to have basic competence, but they also need to be able to adapt those skills as the situation demands. So what can the big advances in AI over the last few years tell us about how to build this kind of interplanetary exploration robot? Maybe looking at this from a pretty high level, there are two big categories of advances that we could think about: data-driven generative AI techniques and reinforcement learning. And these are very broad categories. We can argue about what goes in which category, but roughly speaking, maybe it's fair to say that these are somewhat separate things, using large amounts of data to train models, these days mostly generative models, and using optimization RL to acquire behaviors. So how does data-driven AI work? Kind of pretty basic question for this audience. You can train models that will generate images, generate text, create chatbots, assistants, and so on. But at a very high level, all these systems are modeling a data distribution, P of X or P of Y given X, maybe probability of image given text or probability of text. And this is basically a fancy version of what we see in like introductory statistics class. Of course, if you're modeling a distribution, the first thing you should ask is like, well, what distribution is it? And for the kinds of models that people use these days, that distribution is the things that people put on the internet, the kind of pictures people take, or the kind of paintings people draw, or the kind of text people type on keyboards. So at some very basic level, what these models are trying to do is emulate the behavior of humans on the internet, which already might sound a little scary. But this maybe also explains why things like prompt engineering are such a big deal, because you're essentially just trying to put this model into the mindset of a person who's going to type an answer on a keyboard that you actually would like to see. And that's a little weird. What does reinforcement learning do? Reinforcement learning is actually, in some ways, a very different way to think about the learning problem. Reinforcement learning at its basic level is about interacting with the world, using that interaction to improve your strategy, updating your model, throwing out data that you just collected, and interacting with the world a little bit more. Reinforcement learning methods have been very successful in a variety of settings that look very different from generative AI. Things like playing video games, controlling robots, and playing board games. One of the cool things about reinforcement learning is not that it produces behaviors that look like pictures that people might draw or text that people might write, but that it produces emergent behaviors. So move 37 in the Lee Sedol championship match was impressive not because it looked like something a person might do, but precisely because it was so unlike anything that humans would have done. We look at these paintings and say, well, they're impressive because this is the kind of stuff that people do. We look at RL results and we say they're impressive because they're emergent, they're unusual, they're not what we would expect. They're novel solutions to unexpected problems. So, of course, reinforcement learning has major weaknesses. The real world is very complex. It's not just about solving problems, it's about dealing with complex physical phenomena, objects, large open world environments, other agents, all these things that require not just optimization, but also knowledge, actually understanding what can be out there in the world, exhibiting common sense and so on. And this kind of generalization to very broad, complex settings is actually a big challenge for RL, because classically RL methods are about this kind of iterative optimization procedure where you collect a little bit of data and improve. Methods that are good at dealing with open world environments rely on large data sets. And collecting large data sets every time you want to improve a little bit is very hard. So imagine collecting like an ImageNet sized data set every time you want to improve your agent a little bit. That's pretty much impractical. So where does that leave us? We have these two ways of thinking about these kinds of problems: data-driven versus RL. The data-driven stuff is really great because it learns about the real world from data, but it doesn't try to do better than the data. It's trying to model the data distribution, behave the way that people would behave. RL is great because it optimizes a goal with emergent behavior. but it doesn't make use of real-world data, which makes it very difficult to apply to environments that are outside of constrained worlds with known rules like board games. So data-driven AI is all about using data. RL is all about optimization. So data without optimization doesn't allow us to solve new problems in new ways, which is a big problem if you want to explore another planet. Reinforcement learning, optimization without data is hard to apply to the real world outside of simulators because you need to build up that body of knowledge. So a notional recipe for RL with prior data, if we want to build our planetary exploration robot, might look something like this. Maybe you have data that you've collected here on Earth, maybe data that the robot collected, maybe data that other people collected and gave to the robot. And we want to use that data to build up some kind of initial body of behaviors. And a good algorithmic framework for thinking about this is offline reinforcement learning from existing data sets. And I'll talk a little bit about that in this talk. But once you've built up a model trained on this offline data, then you want to do the next step. You want to actually send your robot to another planet. And over there, you want it to improve through experience. And you'd like this capacity to improve through experience to be greatly accelerated by whatever the robot learned back on Earth. And both of these parts are actually very important because the stuff over there, that's important for utilizing prior data, and that's how we get that powerful generalization open world settings. This stuff is important because that's how, when we encounter some very unfamiliar situation, we'll be able to come up with a novel solution to a novel problem. So that's kind of the notional view of what is, in my mind, kind of an ideal AI agent. And we can think about what steps we need to take to develop methods to make that possible. We haven't made that possible. I haven't sent any robots to any other planets, but I'll tell you about what I think are kind of steps towards this recipe. So I'll talk about some algorithmic fundamentals for offline RL. Those of you that are familiar with reinforcement learning, this will be fairly basic, but I do want to go through some of that. I'll talk about some research in robotics on RL and generalist navigation skills, as well as language condition manipulation. And then I'll talk about a few recent results on even faster online adaptation at the end, if I have a little bit of time. So let's start with some offline RL fundamentals. What do we expect offline RL methods to do? These methods that take data sets and distill them into behaviors. Well, one intuition that people sometimes have that I think is maybe not quite the right intuition is that it's a little bit like imitation learning. So imitation learning is how we often think about data-driven learning-based control. You have data of some behavior you want, maybe going from the green thing to the orange thing, and you train on that data to emulate it and get a policy that does something like that. That's nice, but we'd like more than that. We'd like to use our data not just to copy what was done, but to actually understand what could be done, and among those things, select the best behaviors. And that's how we could do better than the data. So maybe your data looks like this. It shows you a variety of different things you could do in this simple world, and what you'd like to do is figure out how to go from here to here. So you can put together little pieces of these examples and find the behavior that you actually would like to execute. So if we can solve that problem, now we can do a lot better. We can actually take large and diverse data sets that maybe consist of things that we don't necessarily want to copy, but that illustrate what's possible and extract the behavior that we'd like to see. So at a macro scale, you can think of it as, if you've seen examples of going from A to B and B to C, you should be able to figure out how to go from A to C. That's kind of a very simple example of this. But in reality, what would be really nice if this happens everywhere all at once. So if, let's say, you have data from human drivers driving cars, and different people drive those cars in different ways. Some of them are good at merging on the freeway. Some of them are really good at navigating a stop sign intersection. But nobody's really good at everything. If you can take that data and distill out an agent that is as good as the best human in every single situation, they'll be better than any one human overall. And that's basically the same as this kind of A, B, and C example, just applied at a much more granular scale. So we'd really like algorithms that can do that. I'll describe a little bit the algorithmic foundations for these methods. This part will go pretty quick. I don't want to dive deeply into any of the algorithm details, but this is just to get a sense for how this works. For most modern offline RL algorithms, the basic foundation is based on Q-learning. Q-learning is a very simple and popular way to think about RL from off-policy data. A little bit of notation. You have an agent that interacts with the environment. It selects actions A, and the environment responds with states S. The environment also produces a reward R. And the learning algorithm is supposed to select a policy, which is a distribution over actions given states. The objective is to maximize the cumulative reward over the agent's lifetime. And a very useful object for that is something called the Q function. The Q function is a function of the current state and action that predicts if you are in this state and you take this action, and then you follow policy pi thereafter, what is the total reward you will accumulate? This object is very useful because if you can find the Q function for a particular policy pi, you can extract a new policy that is as good or better simply by being greedy with respect to your Q function. So this is the basis of policy iteration, a very classic RL algorithm. You can also short circuit this process and directly train a Q function that is equal to the current reward plus the maximum over the next Q function. That's the basis for Q learning or fitted Q iteration. So these are very classic RL algorithms that are 35 years old at this point. A very, very basic version of this, which is also the foundation of modern deep RL methods, is to simply take this equation, this is called the Bellman optimality equation, subtract the right-hand side from the left-hand side, and enforce it at all states. Of course, we don't have all states, so we use samples. So if you minimize the difference between left-hand side and right-hand side at sampled state action pairs, then you will approximate the optimal Q function. The great thing about this is that this method doesn't actually assume that these states and actions came from any particular policy. And that's what makes it a good foundation for offline RL methods. Okay, so that's the 30-second summary of reinforcement learning. But now, what's the problem? Why do we even need to do algorithmic research on offline RL? Well, the problem is that while in principle, the classic version of this doesn't assume that states and actions came from any particular policy, in practice, the distribution that they came from really, really matters. So that's that same equation up there. And I'm going to write it in a slightly different way. Instead of writing it as a max over the next action, I'll write it as an expected value under a distribution pi nu, which assigns a probability of 1 to the argmax. So I didn't change anything. I just, you plug the argmax in there, that is the max. But this just makes it clear that what matters in order for this to work is that you have to be able to estimate your Q values under this distribution. And if you care about whether your estimate of a learned function under some distribution is accurate, usually the first question you ask is, well, what distribution was it trained under? Because if you test under the same distribution you're trained under, then you expect good accuracy. If not, then you don't expect good accuracy. So what's the objective? The objective is to minimize the difference between the left-hand side and right-hand side of that Bellman equation. So I'm just using y as a shorthand for that. Under the distribution in your data set, I'm using pi beta to denote that. So that's the behavior policy. That's the policy that generated your data. That's that random walk around the 2D plane or the text that people type on the internet. So the behavior policy in general is not the same as pi nu. The whole point is to find a distribution pi nu that is better than whatever generated your data. And that means that you're introducing distributional shift. In fact, it's even worse. Pi nu is selected to maximize the Q value. So it's selected in an adversarial way. Essentially, running RL on static data is a recipe for generating adversarial examples, for generating actions that will fool your Q functions into thinking that they're good, just like adversarial examples in vision. And in fact, if we actually run experiments empirically with this, we find that exactly this happens, that you can easily find actions for which your Q function grossly overestimates the value. The policy thinks it's doing fantastically well, and this keeps spiraling, and eventually everything diverges and blows up. So by itself, this doesn't work. And the reason it doesn't work is because of distributional shift, because you're trying to find a policy that is different from your behavior policy, but training the Q function for it under data from the behavior policy. So that's the basic issue. What can we do about this? Basically, most offline RL algorithmic research tries to deal with this issue in some way. There are a number of solutions that have been suggested. I won't go into great detail about them. I just want to briefly summarize what they are. So there are many different methods, but similar principles seem to be effective. First, use value-based methods, something based on Q learning or Q function actor critic, and then somehow fix the distributional shift problem. And you can fix it a number of different ways. One of the ways you can fix it is actually kind of inspired by adversarial training. Like if the problem looks like adversarial examples, let's fix it with adversarial training. Literally try to train the Q function to patch those exploitable actions that have high Q values. Another way to fix it is to impose some kind of constraint to say, well, if the problem is distributional shift, let's explicitly limit how much distributional shift we allow. And that also addresses the problem. And then there are some exotic solutions, like, for example, avoiding out-of-sample actors entirely during training with some clever algorithmic tricks and so on. So there's some other things you could do as well. I won't go into detail about these, but I will very briefly summarize conservative Q learning, which is that adversarial training style approach, just to give you a taste of how these things work. So the problem is that you have this overestimation because you are finding actions that exploit your Q function as adversarial actions. Graphically, you can think of it like this. This is the true signal. This is your fit to that true signal. The blue fit is good in most places, but if you take the max, you'll find exactly the point where it overestimates the most. That's the problem. So what you can do is you can find those points and just minimize them, and that will push things down. Very simple solution, very similar to adversarial training. This is a simple version of this method. This second line, this is exactly standard Q learning, left-hand side minus right-hand side from before. And this is a regularizer. Find a distribution mu that maximizes Q values and then minimize those Q values. very much like adversarial training. In practice, there's a few little details to get this right, but that's the basic idea. And that can patch this problem to a degree. Now you'll notice immediately there's a number of issues that crop up, like you need to pick a weight on this thing, you need to decide how pessimistic you want to be. And every offline RL method will have some kind of trade-off parameter that, roughly speaking, controls how much you're willing to extrapolate and take a chance versus how much you want to stick to what you know. And you have to select that parameter. That's always there. But that's basically the idea. These kinds of methods have been applied pretty widely to a wide range of things. They've been applied to, for example, training on data from Atari games to learn a policy that can play lots of different Atari games and then fine-tuning it to new games. And that actually works. You can pre-train on offline data and then fine-tune to new games, a little bit like that Mars Explorer, that pre-train on Earth and then fine-tune to another planet, except here the planets are very simple and pixelated. You can, I won't go through this in too much detail. You can apply this to other things, robotic control. I'll actually talk about that a little bit today. You can apply it to dialogue agents, so you can train dialogue agents with offline RL using data of humans talking to other humans, and that will actually allow you to train agents that accomplish tasks. You can apply this to all sorts of more commercial things, like you can do mobile notifications, optimize for click-through rates for LinkedIn. This is something somebody did, not the thing I work on, but it's pretty cool. You can do digital management systems, marketing, that sort of thing. Very natural settings where there's a lot of data available. But what I want to talk about today, more in keeping with the theme of this workshop, is applying this to embodied systems, systems that actually need to act in real-world settings. So what I want to tell you about next is using some of these ideas for training robots that can perform navigation tasks, general-purpose navigation skills. So we started our work on building general-purpose navigation policies a number of years ago. And when we started off, what we did is we collected data from ourselves and also from others that covered a variety of different robots navigating through different environments. And this is a pretty heterogeneous data set. It has robots that are small little RC cars or full-scale ATVs, so that there's quite a bit of variability in the environment in terms of embodiment and so on. And initially, we tried something pretty simple. We just tried to train a policy that achieves goals. So you give it a photograph of where you want it to go. It takes in the current image. It takes in a little context, so a history of images, which it uses to deduce what kind of robot it's controlling, and then predicts the actions that will navigate to a particular location. And it turns out that this actually, by itself, as a pre-training strategy, works decently well. So you could, for example, train a policy like this on these 6 different robots, and it will generalize to other things, like it'll fly a drone through a hallway. It was never trained on drones before. Now, I will confess this drone is pretending to be a car because it's flying at a fixed altitude. But other than that, it is a drone that this policy never saw before. It can fly around hallways and things like that. But this is basically what you could think of as pre-training. So for our Mars Explorer robot, this would be what it trains on from here on Earth. And then from there, well, we want to scale it up a little bit. This is 2024, so we have to use transformers. So of course we did that. And then we can have other embodiments. We can have legged robots and things like that. We can even fine-tune it from there. And this is getting closer to what we want in the long run. For example, we have our encoder that encodes goals. We can replace that encoder after training with something that encodes turn-by-turn instructions, like Google Maps. Turn left, turn right, go straight. And then fine-tune on a little bit of data of autonomous driving from the Carla simulator. And you can actually get something that drives in Carla with a small amount of data in the driving simulator and a large amount of data from all sorts of other robots in the real world. So now this is getting a little closer to what we want. This fine-tuning is not autonomous. This actually uses demonstration data. But we can also try to make it autonomous, and that's where the RL is going to come in. So let me skip this. So the project I want to tell you about here is something we called FasterLap, which kind of reflects what it's doing. So this is going to use that multi-robot data to do offline RL pre-training, and then it's going to fine-tune with online RL for a different task. The task here requires racing around a hallway. It starts off a little bit naive, but after about 15 minutes of training, it's going to actually be able to make laps around this building. This is Soda Hall, 5th floor. And after about 25 minutes, it's going to go pretty fast. Now, a few things I want to emphasize about this. The policy here is controlling this robot entirely from first-person RGB images. The pre-training is on a variety of other robots. So this particular platform, this little RC car, was not seen in the pre-training data. The policy is trained in a total of about 30 minutes to convergence. So this is at the 25-minute mark. After training, it can make this loop at about the same speed as the graduate student who was leading this project if he uses the same first-person camera. Turns out that if the graduate student is allowed to use a third-person camera, so Kyle actually tested this, from the third person, he can race faster than the policy can. But from the first-person view, he's about the same speed. Now, I'm sure there's people that are better at racing RC cars than Kyle is, but it's at least Kyle level for first-person videos. What I think is interesting about this is that in 25 minutes, training a perception system to do all this would actually be pretty difficult. And even the RL process, RL is often thought to be very sample inefficient. So the fact that this offline RL pre-training gets you that capability so quickly, I think is actually pretty compelling. And I think that's something that bodes well for our Mars Explorer. For something more representative of the planetary exploration mission, this is the same system, fine-tuning outdoors. This is also is about 25 minutes. Outdoors is actually physically much more challenging because the grass is bumpy, the camera shakes a lot. It actually figures out that in between the checkpoints, which are on the grass, it can go on the paved path, and there it can go a little bit faster. It's a little bit clearer how challenging this task is when you see it from the first-person view, so this is what the robot is actually seeing when it races around. So this is actually a pretty tricky task. Okay, so that's navigation. Now, this maybe gets us some part of the way towards our Mars Explorer, but we can look at other scenarios too, and we can see if we can build agents that maybe have a richer repertoire of behaviors. So I'll talk about language condition manipulation next. If we want to do this at a larger scale, we might want a variety of different tasks, not just navigation. So we might want real robots that can master hundreds of tasks, and then they need to fine-tune all of their diverse behaviors, not just one. So you want them to actually improve through lifelong learning in the real world, and whatever experience they collect should improve all of their behaviors, not just fine-tuning to a particular situation. So do these kinds of RL ideas still work at a huge scale if we try to really apply them to hundreds of possible tasks? At Google, one of the projects that we were doing earlier last year was to train large-scale language condition policies, initially with imitation learning. So we collected a data set with about 150,000 trials of different behaviors, simple atomic behaviors, with language instructions. This was pretty neat. Like, you could get robots to do things like tell it, go fetch chips from the drawer, and it will figure out that it should navigate to the drawer, open the drawer, pick up the chips. And all of those are language condition skills executed by this imitation learning policy. But I apologize, the resolution here is a little lousy, but take my word for it, it's opening the drawer and taking out the chips. And then we had this question. We thought, well, can this system benefit from autonomous experience? So it had, for this particular experiment, we use a subset of our demonstrations, 38,000 demonstrations. And then we ran the policy autonomously, and we collected trials. Some of them succeeded and some of them failed. We filtered out all the successes because we wanted to study a very specific hypothesis. Can the failed attempts actually help? So we actually removed all the successes intentionally, and that left 20,000 unsuccessful autonomous trials. We added those to our demonstrations, and then we ran an offline RL procedure to see if we could actually get improvement from just adding these unsuccessful trials. And that basically gave us an offline RL trained version of this RT1 system. So the setup here is a little bit involved, because in order to get these language condition policies to work well, we need to use a large transformer-based policy. So we modified it to be able to basically train it with conservative Q learning, which means we need to train the transformer as a Q function. Instead of discretizing different action dimensions, this actually treats every dimension of an action as a time step in an MDP and outputs a discretized action value for it. So basically, every dimension of every action is a separate time step in the MDP, and every discrete bin for that action has a separate value associated with it. And then this whole thing is trained with a variant of conservative Q learning, and it can perform a wide range of these language condition tasks. And the interesting thing about the results is that, so this is the RT1 baseline, this is basically the previous Google project. Just from including those unsuccessful trials, the performance on these tasks went up by over a factor of 2. So those unsuccessful trials are actually really helping with the average success rate. And I know this has 3 different rows, but actually each of those, these are classes of tasks. Within each of them, there are many tasks. So this is actually a pretty significant number of language condition tasks. So the system actually works, and you can actually use unsuccessful trials to greatly improve your success rate. We can apply RL at an even larger scale. So this is now getting more into kind of industrial scale problems. One of the things that we did at Google, we had a long multi-year project on actually using RL to sort recyclables. This actually involved robots navigating through real-world buildings that are actually, like, in use by Google engineers that are doing whatever it is that Google engineers do. And they throw their garbage into the bins, and then the robot is supposed to sort it, put recyclables in one, compost in another, and so on. And this was set up as a large-scale RL system, a little bit in line with that Mars Explorer example, where there's a training phase. We actually called these classrooms. In the pre-training phase, basically the robots are set up in a classroom where they practice their trash sorting. There's also some simulation data that goes into this. And after that pre-training phase, they go out into the real world, and there they have to experience the real trash that real Googlers put into those bins. And this was a very long duration deployment, so we actually have a graph in the paper showing performance over months as it goes up, and it basically does exactly what you'd expect. So while this might not be as exciting as exploring another planet, there's a lot of exciting stuff in the garbage, and there's some nice outtakes in the paper if you want to see, especially around Halloween time, people seem to put some really crazy stuff in there. And these things can kind of adapt to that. So it can't lift the full pumpkin, but it tried to. Okay, so in the last few minutes, what I want to talk about is some more recent work that tries to get much more at the fine-grained aspects of motor skills. So far I described large-scale training experiments that focus on relatively less granular skills and really with an emphasis on generalization. But if we want skills that are very dexterous and very performant, we can actually handle that a little bit as well. So one of the methods that we developed over the last few years, very simple method, is called RLPD, RL with prior data. It turns out to be a very effective RL strategy for very quickly learning dexterous skills. The idea is very, very simple. You have a buffer of offline data, which typically is bootstrapped with a small number of demonstrations. And then you run reinforcement learning and you mix 50-50 data from your current exploration and the offline buffer. There's some concurrent work called hybrid RL that proposes a very similar idea. It turns out there's some nice theoretical reason why 50-50 mixing is actually a really good choice here. I won't go into that in too much detail, but the high-level principle is that if you make a few very careful engineering decisions, you can get this kind of very simple RL strategy to be extremely performant. And one of the things you could do, for example, is you could train, this is an electronic assembly task, you can train a robotic arm to insert this chip into a PCB board. This is a very fine-grained task where it's very easy to bend the pins. And you can actually, if you get all the design decisions right, train this in about 15 minutes. So this entire training process, this is obviously sped up. This video will go out to 15 minutes. I don't think I'll play it for quite that long, but you can see even directly right in front of your eyes that over the course of this training period, it's getting closer and closer to inserting those pins into the PCB board. And this is just the entire training process. There's about 10 demonstrations that are provided in advance. Those demonstrations are not sufficient to solve the task. Once you've trained one of these things, because there's so much noise that happens during the RL process, you actually get a pretty robust policy. You can move the object out of the way and it will actually follow it along. This is another policy for inserting a cable into a clip. You can actually perturb it and it will keep trying. So it's quite tenacious about this. This is a comparison. I apologize for the resolution, but I'll read this off to you. Between blue, which is just imitation learning on the original demonstrations, 10 demonstrations provided for each task, and red, which is after reinforcement learning. After reinforcement learning, for all these tasks, the performance is essentially perfect. For imitation learning, for the PCB insertion, it's about 10%. For cable routing, it's about 19%. There's a pick and place task also, it's around 60% from just the imitation learning phase. It's also a lot faster after RL, and that's kind of an obvious statement. So here, the x-axis is how long it actually takes in terms of time to perform the insertion. It gets a lot faster after RL training. That's exactly what you'd expect. Now, you can also do some neat things with adaptation to new situations with this. So this is a locomotion experiment. Oh, let me restart this. Second. There we go. Okay, so this is a locomotion experiment where this robot is learning to walk. Initially, it learns to walk from scratch with this algorithm. It learns to walk from scratch in about 5 minutes. But the interesting thing is that because the RL algorithm is so fast, once you actually learn one of these gates, you can actually adapt in real time to new situations. So I'll just go through this a little quicker so you can see where it gets to. About 3 minutes in, it's walking. This is from scratch, so this is just learning the gate. It's not the most beautiful gate in the world, but it's pretty quick. But because the training is so fast, when you put it into a new situation, this is a soft mattress. I don't know if it'll find soft mattresses on Mars, but whatever novel situation you might encounter, you can actually adapt in a single trial. So this is the final version of our method. Initially, it's a little bit clumsy, but it does get to the end of the mattress, and is actually making gradient updates literally every single time step of this process. So it makes about 100 updates in one of these traversals. The baseline obviously doesn't get us far, and then we measured things like how long it takes to actually finish the task. If you were not adapting, you would not be able to finish the task, but you can finish it in a particular amount of time if you adapt as you go. And that's where these very rapid RL algorithms can really shine. So whatever weird situation you might encounter, you can actually just keep writing your RL algorithm and keep getting better. Okay, so those are the empirical results I wanted to cover. I wanted to leave off with a few bigger picture thoughts, and maybe that can go into the discussion a little bit. There's an idea that people throw around a lot, which comes from Richard Sutton's excellent essay called The Bitter Lesson, about a kind of a principle that we can use in modern machine learning. I actually find that essay to be very compelling, but I do think it's often a little bit misunderstood. And I think that actually goes to one of the messages that I want to get across in this talk. So a quote from Richard Sutton's essay is, we have to learn the bitter lesson that building in how we think does not work in the long run. The two methods that seem to scale arbitrarily are learning and search. And a lot of people take this quote to mean that what we should do is we should just shovel more data into GPUs and not worry too much about what's going on under the hood. But I think this is often a little bit misunderstood because there are really two words here, learning and search. And these words, they do have a technical meaning, especially the word search in RL, it actually means something. Learning, I think we all know what that means. You use data to extract patterns. So you actually pull something from the world, bake whatever you pulled from the real world into your model, and your model like understands patterns now. Search, roughly speaking, you can think of it as using computation to extract inferences. So learning is about getting something from the world and pulling out patterns. Search is about ruminating on what you've already learned to figure out how to solve a problem. And we often forget that this is actually really important. So search is basically that optimization component. Some kind of optimization process that uses typically iterative computation to make rational decisions. And if there's one message that I'd like you to take away from this talk is that we really need both of those things. And data-driven AI is really powerful for this stuff. And reinforcement learning is really powerful for this stuff. And if we put them together, then we can actually get agents trained on large amounts of data that are more capable than whoever produced that data. So data without optimization doesn't allow us to solve new problems in new ways, and optimization without data is hard to apply to the real world outside of simulators. But if we can put them together, then we can actually maybe move closer to getting that Mars Explorer. I think I'll stop there and go to discussion. Thank you for listening. Yeah.
Sergey, thank you. It was a lovely lecture. For learning, in computer vision, we have estimates of learning efficiency vis-a-vis human learners. For example, for bird classification, my estimate is that humans are about 300 to 1,000 times faster, more efficient than our learning algorithms currently. Now, is there a task in search where you are able to compare human efficiency with machine efficiency to give us a baseline and somehow a point of arrival?
That's a really good question, yeah. I think that would be a very good idea for me to do. I have not done that. I do think we could set up an experiment like that for some of these motor control tasks, like the PCB insertion. I think the confounding factor there is that basic low-level motor control for humans, it's very hard to separate what we know in advance because we're humans from what we're learning in the moment. So if you give somebody like a 3D mouse and ask them to do that PCB insertion, it's really, really hard. But it's difficult to argue that that's sort of the upper limit of human learning speed because it's maybe hard for reasons that like the device is unintuitive to us. So I think it would be really good to try to answer your question somehow, but it's a little difficult. I think maybe if there's anyone in the audience who works on neuroscience and motor control, you might have a much better answer for how to do that experiment. I think it'd be pretty fascinating.
Thank you.
So, in the work on multi-embodiment, where you share a policy or part of the policy between a lot of different robots, and you do the pretraining there, I'm wondering if you have a sense of what exactly is the shared structure that's learned. Like, what degree is it some kind of motors, schemas, or is it actually just more like a nice fuzzy initialization, which is like
or just nice visual features? I think that's a really good question. I think that we do need to do more work to understand this. There's a more recent paper by Jonathan Yang from Chelsea Finn's group at Stanford that tries to combine data from robotic arms and ground robots. And the robotic arms use a wrist-mounted camera, so they kind of look like they're navigating. And he has actually a pretty nice argument in that paper that a lot of what you're pulling out from that shared structure is basic visual servoing primitives. Basically, like if you see a thing in your visual field, can you like servo your camera so that it points at it? Or for obstacle avoidance, do the opposite, servo it away from that obstacle. And he has some nice illustrations for why he believes that is what's happening. But I think there's like a lot more that needs to be done to understand that.
Great talk. Again, and I totally buy this big data and RL as a way to kind of get to the future. I totally buy it. I guess I have a question for you, which is that, look, if anyone sort of gets where we're going to go, you know, I would bet on you. And I guess to me, I have a little bit of a fear too. I mean, I'll put a few things together where it's like you describe, you know, RL can learn things and then behave sort of in really unpredictable, sort of exponentially more capable ways. You use this particular word with regards to the robot that was trained online for 15 minutes in order to do the cable thing, if I understood correctly. You use the word tenacious in, you know, doing that thing, which I think is a word that sort of gets maybe a sort of core, you know, if I have a fear, whether I'm wondering whether I should have a fear it is. And I'm wondering, you know, it sort of seems like if we have these systems, maybe they're going to get very capable and sort of take off in capability. And we use big robots these days, right, even in lab. And I'm wondering how you think about that. Maybe guardrails is a word. How should you think about that?
I think it's a good question. I think my answer here would be that if you want to build autonomous systems where you have confidence that they're trying to accomplish the goal you want them to accomplish, the first step is to make sure that they're actually trying to accomplish a goal. I think the best way to get unpredictable behavior out of your AI systems is to not train them to accomplish a goal. So I think you're right that there's some care that should be taken with this. I think that decision-making algorithms like RL algorithms are a much better tool for this kind of stuff than the kinds of things that we're doing with language models and vision language models, where we're training the system to emulate a wide breadth of human behavior, and then using a fairly crude tool, which is prompt engineering, to elicit certain behaviors from them. So I think that if we can specify a goal and then optimize directly for that goal, if anything, that gives us a lot more control over the outcome that we're going to get. That's not to understate the challenge. I think you're actually completely right, that if you're imagining like training an autonomous vehicle with this kind of stuff, like you need to be really careful that you specified the right objective for it. But I think like not specifying an objective at all is strictly worse than that.
And you think that specifying a safe objective is possible?
I don't think it's easy. I think like my colleague Stuart Russell needs to figure out how to do that because that's what he's working on. So I don't think it's easy by any means, but I think it's much easier than not specifying an objective at all. But I think this is a very good point. I think it's something we should keep in mind.
Thanks for that talk, Sergey. So my question, I guess, is in a similar vein as Petro's, but there's this huge body of literature on sample efficient RL. And I read these papers, and at the beginning, they're like, RL methods require 10 billion samples. And I'm like, great, this is a problem that it recognizes. And by the time I get through the paper, they're like, oh, our method can use 1 billion samples, which is, I guess, an improvement. But my question is, how do you the current paradigm for sample efficient reinforcement learning, you think all we have to do is scale, and we have to take these insights to the end of the line, and then that'll be enough to actually get us to kind of human level efficiency in terms of learning, or what are kind of the paradigm shifts that are needed for us to get actual sample efficient learning from rewards without
I think the key is to be able to pre-train RL systems. So I think that the navigation project that I showed maybe gives a hint of how this might work. That it's actually not a particularly original answer. Like this is exactly what happened in supervised learning too, to some degree. That originally we had big models that we would train from scratch with domain-specific data sets, and we had to work really, really hard to curate those data sets and label them and all that stuff. But once we figured out how to do pre-training properly for supervised learning systems, now we can do supervised fine-tuning with much smaller data sets. It's hard to do that same thing for RL, because for RL, efficient learning of a new skill requires a lot of stuff. Like it requires figuring out how to do exploration and having the right representations and getting all the optimization stuff right. So there's kind of just more things that go into that. And that's why it's a harder problem. But I think the answer ultimately will probably be the same, that if we figure out how to do pre-training properly, then we can get the actual RL process to be efficient.
So maybe I'll push back a little bit, but in terms of, if we look at the great successes that we're seeing, like language and vision, language in particular maybe, these pre-training methods, which work very well and are very general, this next code prediction thing, doesn't seem to solve the efficiency problem. In terms of, we still need supervised fine-tuning, we need RLHF, and there's a great deal of scale that goes into there as well. So is it really clear that we'll be able to kind of do that for robot learning?
Well, I think that it depends on the problem you want to solve, right? So at some level, if you want to solve a problem that requires lots of data, there's just like from an information standpoint, there might be no way out. But if you have a problem that basically requires linking up a little bit of new information to things you already know, which is basically what we get, for example, from in-context learning with LLMs or VLMs, then that prospect, that's a much more tractable kind of situation. It's tractable once you have the right algorithmic framework for pre-training and fine-tuning. And that framework is simple for supervised learning. It's far from simple in RL, unfortunately. I'm not sure who, Pulkit or Pietro?
Yeah, so Sergey, nice talk, nice results. I like the way you're thinking about learning and search. But is this an implication that the amount of search you require is going to be quite small, in the sense that, in learning we have these foundation models, and the search seems to be like a little bit of, fine-tuning.
You're kind of implying we're much better at learning than we are at search. So let's do lots of learning and only a little bit of search.
That's the question, right? And I'm curious, like, some of the examples that you had in the talk were like, if you think about like the car driving or like the chip example, you're almost close to the solution, right?
I think that's right. Yeah.
So if you were to scale it up to higher degrees of freedom or potentially doing the whole task, do you still think it would end up being similar, or do we need something more?
I think this is really like the million dollar question. Like, I think what you just said is like probably like the most compelling criticism of what I presented. And what I would say is that I think if we want very capable AI agents, the thing we should be trying to do is more search and less learning, right? Because in some sense you can sort of think of search as like pulling more capability out of the same amount of data. So if you're worried about how much data you need, the more search you're doing and the less learning you're doing, the more sort of capability you get for the same number of examples. But I think you're completely right that where we're at now is actually not that good. That probably most of the firepower comes from this, and then there's like a little bit of icing on top from this.
What do your thoughts sound like a foundation model for search instead of a foundation model for learning?
Yeah, that's a good question.
Yeah.
I don't have more than idle speculation for you on that. Like I could speculate and say like, well, I talked about how we can use offline RL followed by online RL, so maybe something like that is like a good recipe to start with. I think maybe the real answer for anyone in this room who's interested in this is actually setting up the problem properly. I think one of the issues that we run into if we actually want to study this recipe for real is it's hard to set up things outside of relatively toy domains where we can like actually make serious progress on this. Because with these robotics, I love working on robotics, but there's so much system level challenge that you run into that by the time you get into the point where you want to make fundamental improvements over here, there's sort of a lot that's, well, I mean, you know this as well as anybody, there's kind of a lot holding you back because every little brick that you move kind of topples the whole edifice. So actually setting up the problem in the right way, figuring out the domain where it's easiest to make progress on it, that's probably the thing that would most unlock this. And I've been experimenting with ways to do this. I know you've been experimenting with ways to do this, so more work is needed there.
Okay, let's do one last question, and then we'll break for lunch. I don't want to hold people.
Yeah, so it's the great talk, Sergey. So this is not a trick question at all, but I'm trying to understand basically what your opinion is of why industry is still not there with self-driving cars, given what you're presenting, which I agree with, by the way, more or less.
Yeah.
What do you take there? Is it something that do you take that as evidence that something is still missing past what was presented here, or is it that they're just making the wrong bets? I'm just very curious.
Yeah. It's a very good question. I think my instinct is to say something similar to what I said to Pulkit in regard to his question, that there is a process challenge here, that effective machine learning systems typically require a lot of engineering and very large scale. And when you get a system to, especially if you're doing autonomous driving, if you get a system to that point where it's training on like, billions of examples and there's a complicated kind of infrastructure supporting it, it's very difficult to maneuver that thing in various ways. So it's especially when it comes to things like algorithmic exploration, which kind of sits at the very top of this thing. So if you want to build, if you are an engineer and you want to build a modern machine learning system, probably experimenting with algorithms is the last thing on your mind, because experimenting with algorithms is going to maximally destabilize everything. So I think I think the issue here really is one of process, where if we want to explore novel ideas for making this stuff work, and we want to do, and those ideas fundamentally change their character at scale, that's almost like the toughest kind of research setting to work in. So maybe what we should actually be thinking about is the right process to set up experiments and kind of experimental infrastructure for studying these kinds of things. And I have some ideas about how to do that, but I think it's genuinely very hard.
Okay, great. Thanks. Okay. And now we have lunch until 1:30.